Hello folks, this is a part 12. It's the last part of our exercise 4.1. Here one problem will be a divisibility problem and one problem will be an inequality problem. So that is our problem number 23. What does it treat? 41 raised to n minus 14 raised to n is a multiple of 27. That's what the question says. So right away, let P of n represent the given mathematical statement to show that P of 1 is true, which means you have to show that 41 raised to 1 minus 14 raised to 1 is a multiple of 27. You need to show this. So let's consider this. 41 raised to 1 is 41 minus 14 raised to 1. All that is 41 minus 14 itself. What will it come to? 11 minus 4 is going to come to 7. 3 minus 1, directly 27. Oh my god, it's direct. 27 into 1. It's a multiple of 27, right? So therefore, 41 raised to 1 minus 14 raised to 1 is a multiple of 27. So that is how P of 1 is true. Assume that P of k is true. So what do we know? We know that 41 raised to k minus 14 raised to k is 27m. That's what we understand by multiple. Now comes our characteristic equation 1 by pushing things on the other side. So let's take this on the other side. So you'll get 41 raised to k, 27m plus 14 raised to k is your 41 raised to k. To show that, so that is our equation 1 from here. Then you have to show that P of k is true. Sorry, P of k plus 1 is true. So what do you need to show? You need to show that 41 raised to k plus 1 minus 14 raised to k plus 1 is a multiple of 27. So let's consider this. So let's consider 41 raised to k plus 1 minus 14 raised to k plus 1. So that is like 41. A raised to m plus n is a raised to m into a raised to n. So it's 41 raised to k into 41 minus 14 raised to k into 14. So we are taking our equation 1 now. Instead of writing 41 raised to k, we'll write 41 into 27m plus 14 raised to k. What we have done here, we have used our equation 1. So what happens? Let's open it up. You'll get 41 into 27m, then 41 into 14 raised to k minus 14 into 4 raised to k. 14 into 14 raised to k, I'm sorry. So you have these two as like terms. What is the advantage? 41 into 27m plus 14 raised to k is common. Let it go out. 41 minus 14. 41 minus 14 we know is 27. So what comes? 41 into 27m plus 14 raised to k into 27. You can have 27 common. We are left with 41m plus 14 raised to k. So it is actually 27 into something. That means it's a multiple of 27. So what we get over here, 41 raised to k plus 1 minus 14 raised to k plus 1 is a multiple of 27. Is a multiple of 27. What does that mean? That pk plus 1 is true. So from steps 1 and 2, given mathematical statement is true by PMI. So that finishes our problem number 23. We'll quickly take up the problem number 24, which I told you before is an inequality problem. So problem number 24. Let's see how it reads. We can have this erased. We don't want these steps. So let's see how it goes. Problem number 24. It says 2n plus 7 is less than n plus 3 the whole square. You've got to show that 2n plus 7 is less than n plus 3 the whole square. So as usual we can start. Let Pn represent the given mathematical statement to show that P of 1 is true. That means what do you have to show? That is, you will in essence you have to show 2 into 1 plus 7 is less than 1 plus 3 the whole square. Let's consider the left hand side and see what happens. The left hand side comes to 2 into 1, 2 plus 7, which is 9. And let's look at the RHS. The RHS says 1 plus 3, 4 squared, which is 16. In practice, we know that 9 is less than 16. So we have got LHS less than RHS. That's how P of 1 is true. So you have got P of 1 to be true. That is over. Now step 2, assume that P of k is true. So if you know that P of k is true, that means you know that 2k plus 7 is less than k plus 3 the whole squared. So that is about our P of kth step. Obviously, what do we have to show next to show that P of k plus 1 is true? So what do we have to show? We've got to show wherever x comes, wherever k comes, we're putting k plus 1. So it will be 2k plus 9 less than k plus 1 plus 3, it's k plus 4, the whole squared. You need to show this. So in order to show this, let's consider this 2k plus 9, or the LHS if you want. You can consider 2k plus 9 raised to 2. Let's see how that, it's only 2k plus 9. So let's consider 2k plus 9. This is what we need to show. They ask us to show this less than k plus 4 the whole square. Now 2k plus 9 basically is 2k plus 7 plus 2. We could do it that way. Then only we are able to use equation 1. What happens? From 1, it's clear to us that 2k plus 7 is less than k plus 3 the whole squared. How do we get this? We get this from 1. Now what do we do? Since you know that this is less than this, we don't have much options, but let's open it up and see what happens. A plus b the whole squared, a squared plus 2ab plus b squared. So this comes to 6k plus 9 plus 2, or rather it comes to k squared plus 6k plus 11. Not much things to do. You know that you have got to show it to be less than k squared, k plus 4 the whole squared, which means what? It is k squared plus 8k plus 16. So we just use our common sense. It's very clear to us that k squared, of course the value is the same. 6k is always going to be less than 8k. That's obvious. 6k is going to be less than 8k. And 11 is always going to be less than 16. So what happens is k squared plus 6k plus 11 in practice is less than k squared plus 8k plus 16. And that fortunately happens to be k plus 4 the whole square. So in effect, what have we got? We have got 2k plus 9 to be less than k plus 4 the whole square. Now having got this, what have we got? This is exactly our pk plus 1 statement. So p of k plus 1 is true. So from steps 1 and 2, given mathematical statement is true by principle of mathematical induction. This is how we are going to complete our inequality problem. 2 inequality problems we have come across. This is how we are going to go about doing it. That is our exercise 4.1, and that finishes our chapter. In the next video, we come with the new chapter. Thank you.